Beautiful. All right, here we are. So I shudder to think what the campus must look like right now after all that rain. I would imagine that there's a lot of trees down that whole path along Anderson Hill Road. Often when there's bad weather, the trees fall all over the place. Luckily, this class was already online anyway, so we didn't have to worry, but still, um, I'm glad that today of all days that we're definitely online. So did anyone, well, I guess you didn't have to drive in for this class, but has anyone been on the road today? No, you're all at home. Well, that's good. That's very sensible. Okay. All right. So here we are again. Now, last time we started chapter 5A and we got pretty far into it. We spent looking at, and so just to make sure we haven't forgotten what we learned, I'm going to make up an example or two right now, just to get us back in the swing of things. So let's see, where were we? I think we just did 72 and 180. We'll save this one for, yeah, that'll come next. Right now, let's say one more, just to make sure you remember what we did. What is the greatest common factor of, let's say, 120 and 180? Okay, so if you recall, in my opinion, at least, our best strategy for doing this is to draw the tree where you break up each number into not just factors, but prime factors. And remember, what we're looking for is what prime factors do they have in common. That's how we know what the greatest common factor is. All right, so now I know it's been 3 days. Let's see if you can remember. You still have your notes in front of you. So why don't you give it a shot, take a shot at this one and see what you come up with. Okay. I'll move that up here so I can draw a picture. All right, so now remember what we're trying to do here. We're looking for prime factors. So for an even number, your best bet might be to start with 2, although it's not necessary. You can do whatever order you want, because no matter what order you do this in, you'll always get the same result anyway. So I'm helping you here. Remember how this works. And the question is, when do you stop? 60. All right, so we have one person who says 60. Okay. And so we keep going until we have all prime numbers. So the factorization here could be written as 2 times 2 times 2 times 3 times 5. And over here, we'll do 2, let's say 2 and 90, 2 and 45, 5 and 9, 3 and 3. Okay, so the greatest common factor, so the factorization on this side is 2 times 2 times 3 times 3 times 5. And so what we're searching for is, what do they have in common? Okay, so it looks like they both have a pair of 2s and a pair of 3s. No, sorry, only one 3. And 3 and 5, that's right. Okay, 3 and 5, I see it now. So the greatest common factor is the product of those terms, 2 times 2 times 3 times 5, which is indeed 60. And we're done. Wow, that's nice and easy. So this is one way you can do this. It's not the only way, of course, but I think it's probably the most efficient way. So now I do want to show you, though, a very strange case that you might run into. All right, so I think we all understand this technique. But once in a while, you run into one of these very strange cases. Like, what about something like this? 13 and 19. Now, both of these are prime numbers. You could try to create a tree, but if you do, you're just going to wind up with 1 and that number itself because they're prime numbers. Now, what do we do? So what happens is, formally, we say here that when this happens, the greatest common factor is formally defined to be 1. Okay, in other words, they do not have any prime factors in common. Remember, 1 is not prime. So formally, we will define their greatest common factor to be 1. Okay, so if you do run into this in a problem set or something, there's no prime factors in common, so the answer is simply 1. Okay, so that is a special case. And also, and this is just terminology, you don't have to memorize this. We would then say further that 13 and 19 are said to be relatively prime, which means they're prime with respect to each other. It's an interesting way of looking at it because this can actually happen with non-prime numbers. So this is an unusual case, but if it does happen, just remember the correct answer is simply 1. Most of the time that won't happen, but it can happen. All right. So you avoided that. Now, by the way, there's nothing to stop us from doing this with 3 numbers. Okay, in other words, it's possible that 3 different numbers have a greatest common factor. So once again, because we're getting pretty good at this, why don't you figure out what is the greatest common factor between 24, 72, and 120? The technique is exactly the same. You'll draw the tree, you'll find the prime factorizations, and then you'll look for what do they have in common. Okay, so I'm going to do this on a separate slide. We have 72. Oh, wait, 24, 72, and 120. All right, so once you take a minute and figure out what is the greatest common factor of those 3. Okay, so we have a couple of people saying 24. All right, we may as well get started on these trees. Yeah, by the way, didn't somebody ask me about that the other day? Was that this class? Somebody else showed me or mentioned this in another one of my classes, and I still don't know exactly how it works, but apparently if you do just say, please do the closed captioning, and I say yes, it just works. I don't understand the technology, but so if you want closed captioning, just ask, okay? All right, so for 24, we have 2, 2, 2, and 3. For 72, let's see, 2 and 18, 2 and 9, 3 and 3. Actually, there's plenty of room up here. Let me write the prime factorization up here. And here we have 2, 2, 2, 3, and 3. And then 120. Okay, so for this one, we have 2, 2, 2, 3, and 5. So they all, wow, look at that. They all have 3 2s. And they all have a 3. So guess what? The greatest common factor is in fact 24. There's no reason why that can't happen. It is the largest number that evenly divides into 24, 72, and 120. So we have our winner here. Look at that. All right, so I think we're getting a pretty good feel for this. By the way, before I forget, I mentioned the other day that I do have a series of very interesting videos for us to watch throughout the semester. And in fact, we're going to have 2 of them today. 2 very interesting looks at the history of math. And so we'll do that fairly soon. I don't want to completely forget it, but don't you worry, we'll get to that. And I think you'll find that they are very interesting and they start to give you another way of looking at numbers because, you know, it's easy to take them for granted, but somebody had to invent all the numbers that we use and all the operations and everything that we take for granted in math. Somebody had to come up with that idea. So the question is, where did this information come from? And you'll see that it took many, many centuries to come up with what we have today. It was a very long path from, you know, early days of humanity when numbers weren't really needed until now when numbers are everywhere. All right. So what's next? Now, by the way, at some point in your math career, when you were introduced to this concept, almost without fail, you were also introduced to another concept, which will also look very familiar when I show it to you. And that concept is the least common multiple. Does that sound familiar? Why, yes, it does. Now, this one I think is a little bit simpler. But what we need to do is first remind ourselves, what do we mean by the word multiple? Okay, so basically multiples are simply products of a number and all of the natural numbers. So for example, the multiples of 18 start with 18 itself. Then we have 36, we have 54, and you can see what's happening is all I'm doing is multiplying 18 by the natural numbers, and I can keep going as long as I want. Okay, I could do 5 times 18, 6, 7, 8, etc., etc. Okay, so what about 24? Let's take a look at 24. These would be the first 4 multiples of 24. And what we would like to do is take 2 numbers and figure out what is the smallest multiple that they share or have in common. So let's say we're interested in finding the least common multiple of 18 and 24. So I think, in my opinion, the easiest way to do this is literally just write out the first few multiples and keep going until you find the one they have in common, or the smallest one. Now, some people have in the past showed me techniques that they were taught that I was not familiar with. If you've learned another way of doing this, you can feel free to keep using it, but it might be easier to just simply, like I've done here, write them all out. And you can clearly see here that they stop at 72. In other words, 72 is the smallest multiple that they both have in common. There are other multiples they have in common, but this is the smallest one. And so therefore we say that 72 is the least common multiple of 18 and 24. And that's all there is to it. Now, when we get to the first problem set, you'll see some interesting applications of this. You might think, well, so what? But there's always applications of everything that we learn in this class. And you'll see. Oh, here we go. So why don't we try this one? Now that you've seen the trick, you know how this works. Why don't you try this one? What is the least common multiple of 72 and 180? All right, I'll give you a minute and see what you come up with. Oh, here we go. I wasn't paying attention. Yes, 360. Let's see if that works. So what I did was I listed them all out. I stopped after 5. You know, I just sort of randomly stopped at 5. I could have kept going for a while, but I suspected that I didn't need to go any further than that. And I was correct. And you can see that 360 is in fact the least common multiple of both of them. And that's all there is to it. So it's a little bit simpler than I think the greatest common factor. All right. Oh, what do you know? That was it for part 5A. Okay, so now we're ready for 5B. The reason why, by the way, the reason why they're broken up into pieces is because sometimes when in the past, I used to email these to the students before we had anything online. And sometimes when you try to email bulky files, it can be a real problem. So anyway, so let me go get 5B, which is on Moodle. Let's go get Moodle open. Here it is. Okay, so now we're going to add some new information to our real number line. Yes, the other day we introduced the natural numbers, which of course you remember were the numbers 1, 2, 3, 4, 5, et cetera, et cetera. These are often called the counting numbers because of course we use these numbers to count. So now what we're going to do is add to that set the 0, just 0. Now you might not think this is a big deal. It took a long time before humanity came up with the idea of 0. Okay, it was a long struggle because, you know, intuitively, you know, if your only interest is counting up how many chickens you have in your farm, why would you ever need a 0? Okay, so it was quite a long time before anybody realized how important this was. So by adding 0 to the natural numbers, we now have a new set, which is called the whole numbers. And again, this is just the natural numbers plus the 0. Okay, and it of course represents nothing, but it also is used as a placeholder because we have a base 10 system, and every time we move to a new place, we need a 0. In other words, the difference between 10 and 100 is a single 0. So that turned out to be a huge deal. In fact, interestingly enough, as you'll see in our videos today, the idea of 0 actually met with a great deal of resistance in the Roman Empire. And so it took quite a while before Western mathematics had the 0. Now, in addition, if you notice here, we still are missing the negative numbers. Now, you can imagine this was quite a breakthrough. How in the world would anybody come up with this idea of negative numbers? I mean, again, if you're in an agricultural society, what does a number like -3 even mean? Well, it might represent the idea that you owe somebody money, for example. Let's say the balance in your checking account is -$3. That means you have a debt. Now, in an agricultural society, you're not likely to have debts. You have your chickens and your cows and all the rest, and you raise them. But it wasn't until later when banking really got going that the concept of negative numbers started to become important. So by adding all the negatives, we now have a new set called the integers. And if you notice here, I've got ellipses going both ways, in case you're interested. Ellipsis is a singular. The plural is ellipses. And so you notice here we go all the way up to positive infinity, and here we go all the way down to negative infinity. So these are the numbers that do not have a fractional component, but we do have, for the first time, negative numbers. And again, that was a major breakthrough in the history of mathematics, the concept of negative. A lot of things wouldn't be possible if we didn't have negative numbers. Like I said, debts. It would not be possible to have the concept of owing money without negative numbers, and therefore banking would be impossible. All right, now we've got a handful of other definitions here that I want to show you before we dive into something new. These are things, again, you've seen them before. You know, I don't want to really overemphasize memorizing definitions, but there's certain concepts that we should be familiar with. Now, here's one that's going to catch you by surprise. Sometimes in math, adjectives mean something very different than what they mean in everyday life. Here's a perfect example of that. The word opposites. Now, you know what opposites mean. I mean, things that are very different from each other. You know, you probably have met people where you say that, well, they're very opposite from each other. They're very different personalities. But here, all it means is that they have different signs. We have two numbers, for example, 3 and -3, and the only difference is their sign. And in math, we say that they are now opposites. Okay, so when you hear that word in math, it means you have two numbers that are identical except for their sign. All right, now this next one you're very, very familiar with, and that is the concept of the absolute value. What is that all about? Well, that is a case where what we're basically doing is we're dropping the sign. In other words, the absolute value of +2 is 2, and the absolute value of -2 is also 2. There's essentially what we're doing is getting rid of the sign. And for many applications in the real world, negative numbers really don't make any sense. So we often find ourselves getting rid of the negatives by using absolute values. Okay, so you might also recall that when you graph the absolute value of x, it actually ends up looking like a big V. Maybe you've seen this, maybe you haven't. This is the function y equals absolute x. And I haven't drawn it as well as I might have, but that's roughly what it looks like. Now, I don't think I did this the other day, but there's an excellent math website that I'd like you to be that could help you out with a lot of these problems. We're going to go look at it right now. And that wonderful website is called Symbolab. I guess it stands for Symbolic Laboratory. I don't know that for a fact, but that's what it sounds like. And why is this so good? Because it has all this functionality built into it. Among many other things it can do for you is it can actually draw graphs for just about any function you could imagine. So why don't we do this? Let's type in y equals absolute x and then hit go so it knows what function we're talking about. And then right about here, among all these many complicated things it can do, is the word graph. And voila, there's your graph. Look how cool that is. Now, I don't know what this means, view interactive graph. Let me try that. Oh, I see. You can zoom in on it and out. Okay, all right. Well, I'm not sure how helpful that is. But so now you can visualize what this actually looks like. And I think that could be very helpful in understanding what some of these features are all about. Okay, so yeah, there's all kinds of good stuff it can do for you here. But it's one of the more important things is that it can help you visualize what a function looks like because it'll do the graph for you. And you can see there's no negatives. All right, it's not possible to have a negative number here. So, but you can also see why it looks like a big V. For example, this is 2 comma 2, and this is negative 2 comma 2. In other words, we have two values of x which have the same value of y. So that's why it looks like a big B. Interesting. Now, here's something that you might not have thought about for many, many years. You don't usually see fractions as much as before there were calculators. Fractions were used a lot more widely than they are now. Now everything is typically done with decimals because calculators can figure out the proper decimal equivalent of all these fractions. For example, you know that 1/3 is actually the same thing as 0.33333. 2/5 is the same as 0.4. Now these other two, I don't know offhand. 5/19, let's see, that turns out to be approximately 0.26315. And then 6/22 is about so in this day and age, typically we express numbers with decimals rather than fractions, but that wasn't always the case. In fact, here's an interesting side note. Until surprisingly recently, stock prices were quoted with fractions. For example, the price of a stock might have been quoted as you might have seen it quoted as 101 and 1/8. The decimal equivalent of that is 101.125. Now, these fractional quotes were used for historical reasons, which we may discuss one day if we have a chance. But at some point, it was becoming very clumsy to use fractions with computers. And so at some point, the decision was made that just from now on, always let's use decimals. It's just not worth the trouble to deal with these fractions. So, and in fact, in the early days of the United States, in the colonial days, there was a very severe shortage of coins. And so what would often happen, and in fact, let me just show this to you because I think you'll find this to be very interesting. Let me see if I can find it on the internet. Let's see, maybe not. Oh, I was hoping I could find a picture of this. But all right, well, maybe not. But what was happening is in the colonial days, there was a severe shortage of coins, in particular because the British colonies mint their own coins, and there wasn't enough silver anyway. So they were using Spanish silver dollars as a form of money, but there wasn't enough change. So what would happen is if you walked into a store and you wanted to buy something that was, let's say, a quarter of a Spanish dollar, you'd give them the Spanish silver dollar and they would literally cut a slice off the coin and hand you back the rest as change. So the price of this item would have been listed as 1/4, meaning a quarter of a Spanish dollar. And so that's literally how they had to make change. And now this is the 1700s, by the way. Eventually, they started to be able to produce more coins, and it wasn't such a big deal. But in the early 1700s, mid 1700s, it was a real problem in the colonies. There just wasn't enough coinage, and so they had to resort to making change by absolutely just taking these Spanish silver dollars and cutting them up into pieces. And so prices in stores tended to be quoted in fractions that could go down to as small as 1/8. That's about as small as they were able to cut the coins. Beyond that, it got to be a little too difficult, I guess, to do this properly. So each coin is cut up into 8 slices, and so prices were typically quoted as 1/8 of a dollar, 1/8 of a Spanish silver dollar. And that's how stock prices started being quoted in fractions. And they didn't change that until literally 20 or 30 years ago. So you might find that interesting. So yeah, one day I'll try to find an actual picture. See, these are pictures of the coins that were circulating in the United States, or at least the colonial United States, even before we became a country. But they don't seem to have any pictures of them cut up into little pieces, which is kind of, no, I'll find it. But yes, that's what had to be done. Anyway, but let's get back to the math. When you see, oh, by the way, in case you've forgotten, when you have a fraction like this, the number on the top is the numerator. The number on the bottom is the denominator. I doubt that you've forgotten that, but I just want to mention it. It's not impossible. Because like I said, you really don't see a lot of fractions anymore with the advent of computers. So what they're telling us here is that if the numerator is smaller than the denominator, we call that a proper fraction. Mainly the reason for that is because it can't be reduced to something simpler. So we call it a proper fraction. That doesn't mean that it's very polite. That just means that you cannot reduce it, or at least it's not likely you'll be able to reduce it any further. So what do you suppose is the opposite of proper? Improper. So therefore, it must be the case that if the numerator is larger than the denominator, we call that an improper fraction. Okay, now where these names came from, I do not know. Okay, it's not really that big of a deal, but it's also, you want to understand these terms when you see them. All right, and now finally, that leads us up to the next definition, the mixed number. So 1 and 2/23. This is a very awkward thing to deal with. Usually when you see something like this, your natural instinct is to convert it into something simpler. So here, for example, what you could do is you could recognize that this equals 1 plus 2/23. Whoops. And guess what you can do? You can always rewrite this 1 as an equivalent fraction. Let's try 23/23. Now these two numbers have a common denominator, and I can simply rewrite this as 25/23. So most of the time, if you have a mixed number, a mathematician at least would consider this to be, sort of an awkward expression and would most likely convert it to a fraction like this. But even then, the next logical step would probably be to convert it into an actual decimal. But failing that, at the very least, most of the time, you would take your mixed numbers and turn them into fractions. Okay, so it's always possible to do that. And I would say that most likely you'll agree this is preferred to this. It means the same thing, of course, but it's just aesthetically more pleasing, I guess. All right, so those definitions are done. Now we're going to get to something that you know and love, the order of operations. Now, you may at some point have been taught this little mnemonic device. It's called it might look familiar to you, PEMDAS. Does anyone know what those letters stand for? Does that ring a bell? Or has it been too long? I'm asking you to think back many years now. It's early. Oh, right. But what I meant was, what do the actual letters stand for?
Parentheses, exponents, multiplication, division, addition, subtraction.
Okay, very good. And yes, some people remember it as the please excuse my dear Aunt Sally. Whatever it takes. That's the thing about mnemonic devices. Whatever it takes, just use it. If it sticks in your memory, just use it. But now why is it written this way? Why isn't it not sad MEP or something like that? Why is it in this particular sequence? Aha, because these represent the order of mathematical operations. In other words, whenever you have any mathematical expression, the parentheses are always evaluated first. Then we do exponentiation. Multiplication and division, or there's a tie here basically between these two. Here within these two, it doesn't matter which comes first, but these come before addition and subtraction, which are also at the same level of precedence. So this helps us make sure that when we evaluate a mathematical operation, that we do not make any mistakes. We do not get confused about what's supposed to happen next, because the order makes a great deal of difference to the value that we end up with. So like, for example, let's look at this one. Now, what is this supposed to mean? Based on PEMDAS, what would you say is supposed to happen first? Aha, look, there's an exponent. That has to come first. And then once that's done, there's a multiplication that has to come next. And then finally, there's an addition, and that comes last. So this means 3 squared, which is 9, times 3, which is a total of 27. And then finally, at the end, we had 4 to come up with 31. So if you type this into a program like Excel, which you may not have ever used, but you almost certainly have access to it, either on one of the school's computers, or if you have a laptop of your own, you probably could get a free copy of Excel from Microsoft because you're a student. If you were to type this expression in there, you're going to wind up with 31. In fact, we can put this to the test with PEMDAS, Symbolab. Let's go back and check out Symbolab and see how it reacts to this expression. All right, where are we? So we're going to say, I think I have to use the y first. Y equals 3 squared times 3 plus 4 and the solution, oh boy, are these guys helpful. Look what it did. It broke it up in pieces. I didn't even realize it was able to do this. It's showing you step by step. Well, what happened? I squared the 3 first. Then I multiplied it by 3. Although they overcomplicated here by writing 3 cubed. But still, you get the idea. 3 squared times 3 means 9 times 3 or 27. Plus 4 brings you to 31. Now it says here, click to practice linear equations. What is that going to get us? Well, let's try another one. Let's try 4 times 2 to the 4th power plus 7. Okay. Oh man, it doesn't seem to, I'm not sure what that was supposed to accomplish. That's pretty annoying. Well, I'm going to copy it back into the previous page then. Man. Well, before I enter it, what do you think we're going to do? How do you suppose we're going to evaluate this? In fact, I'll tell you what, let me copy this into a PowerPoint slide so we can examine it more closely. Here we go. Oh my God. Well, that's not what I was expecting to see. That must be, you know what, that must be how it represents this internally. Okay, so I'll just type it out properly. Hold on one second. So I actually have access. Now, this is something that, well, you may not want to spend money on this, but I have what's called an equation editor, which enables me to type fairly sophisticated equations. Let's see, what did I use? It was 4 times um, 2 to the 4th plus 7. All right, so I'll put that in there. There we go. Okay. So what should we do first?
The exponents.
Yes. Now it turns out that 2 to the 4th is 16. Okay, so I'm going to replace this with 16. And now what do you suppose comes next?
4 times 16, right?
Yes, exactly. So that will be replaced with 64. When it wakes up, okay. And of course, now I can add, and I'll end up with 71. It's a little slow today. Okay, I see. Okay, now let's go back to this example again. What I've done is I've made a slight change to it. I've introduced parentheses. So let's see how that affects our results. Okay, so now imagine that remember here it was 3 squared times 3 plus 4, but now I've got parentheses. So how's that going to change my results, do you think? What has to be first?
You do the parentheses first, so it's
Exactly.
7 times 3
That's
squared.
exactly right. And now I'm going to do the exponent. And now I'm going to do the multiplication. And that's 63. Now remember, before it was 31. Now it's 63. You see, the parentheses make a great deal of difference. So the parentheses override any of these operations. Parentheses mean that do this first, no matter what it is, even though it's addition, you want to do this first because it's in parentheses. So that's why that is considered to be the highest order of precedence. That's always followed by exponentiation. Then we do both multiplication and division, and then finally addition and subtraction always come last. All right, so I'll tell you what, let's do another one. As far as I'm concerned, more practice is better. Okay, so let's try. Ooh, oh boy, I've got a real, this one's a little bit messy. So why don't you give that one a shot? All right, what comes first? The parentheses. Then we can do the exponent. Then we can do the multiplication. And then finally, we add. Now, let's do an interesting experiment. Let's see what would have happened if the order of the parentheses was a little bit different. Oops. I don't want to change it too much. Well, that looks a little weird, but you do the multiplication because it's in the parentheses, and you'll end up with 107. Okay, so this has to come first because it comes within parentheses. All right, so yeah, we'll be doing a lot of practice problems, so you'll get plenty of practice before we even think about doing any exams, which is good because, you know, obviously this is the kind of material where practice makes perfect. Oh, somebody had it. Okay, sorry, I didn't see your message. Yes, Mateo did get it correct. Very good. You know what's interesting? I don't know what's going on. It used to, this software used to flash orange when somebody made a chat. And it doesn't seem to be doing that today. But all right, well, I'll just keep an eye on it. Maybe I'll just keep it over here at all times. All right, now I'm going to introduce two new concepts very quickly. And then I want to show you those videos that I mentioned earlier because I think you'll find them to be extremely interesting and exciting. And we'll delve into this topic a little more deeply when we're done with the videos. But so far with all the numbers we've been looking at, you notice one thing was missing. Even when we were looking at the integers, we now have 0, we now have negative. What's missing from here? Is there any type of number that you have seen that is not in this list? How about a number like 2/3 or 0.7? That's right, the fractional values are missing here. They will be introduced very soon, but it turns out though that we can classify those numbers in two different ways. So we're going to start out by introducing what are called rational numbers. Now here, the key is the ratio. When, you know, it's like so many other cases with math, when you use this word in practice, in the real world, the rational, it often means that you are, let's just say that if you are rational, it means that you make sensible decisions, that you do things that make sense. You know, like you don't do ridiculous things. You make sensible decisions. And so here it means something different. The key word here is ratio. So a rational number is any number that can be expressed as the ratio of two integers. So here's an example. It may not seem like it, but 2.4 is a rational number because I could just as easily rewrite that as 12/5. And clearly 12 and 5 are both integers. How about negative 1.9? Is that rational? Yes, because I can write it as minus 19/10. So the rationals can be both negative and positive. As long as I can express them as the ratio of two integers, then that number is said to be rational. Okay. Now, you might wonder, now almost without fail, when we have a new definition in math, there are always going to be one or two cases that give us a little potential trouble. Often that number is 0. So it turns out that we will define 0 to be a rational number because in principle, it can be written in many different ways. For example, 0/1. And since 0 and 1 are integers, based on the definition we've just seen, 0 must be rational. Now, in terms of English, what is the opposite of rational? Like, let's say a person who goes outside in bare feet when there's 8 feet of snow on the ground. I don't know. In other words, something that isn't normally what you'd expect to see. Irrational, exactly. Irrational is the opposite of rational. So if there are rational numbers, there must be irrational numbers. What do you suppose we're going to, or how do you suppose we're going to define irrational numbers then? Well, if a rational is the ratio of 2 integers, an irrational number is one that is not expressed as the ratio of 2 integers. And in fact, you already know one of them. Our old friend pi from high school is an irrational number. It is not possible to find 2 integers whose ratio equals pi. Oh my God. Now, this one you might not have seen before. E is another one of these numbers that, like pi, it has an infinite number of non-repeating decimals. It is also considered to be irrational. And how about this one? The square root of 2. Ooh, look at that. That is also irrational. Now, we're going to see a video, by the way. And it turns out that in ancient Greece, where a lot of what we know today in math was invented, this discovery led to a lot of controversy. You might not think it's possible for people to care that much about numbers, but in ancient Greece, they took their math very seriously. And so, yes, soon enough, we'll see a video which talks about how and why this caused problems for the ancient mathematicians. Okay. Yes, it was very controversial. So anyway, we're not going to do it right this minute, but we're going to look at techniques that help us identify which numbers are rational and which ones are irrational. Because it turns out that all real numbers must be rational or irrational. It's not possible to be both, but it's also not possible to be neither. Every one of those real numbers is either one or the other. Now, that leads us up to an interesting thought. And we'll address this more later on, but I just want to leave you with this thought before we start looking at our videos. This might be something that, well, it might cause you to have nightmares when you think about it. The set of real numbers is infinite, obviously. The set of rational numbers is infinite. The set of irrational numbers is infinite. The set of rational and irrational is the real set of real numbers. So what's going on here? We have 2 infinite sets, the rational and irrational numbers, which when we combine them, form the real numbers, which are also infinite. Well, how is this possible? We're combining 2 infinite sets, and the new set, the real numbers, is also infinite. How can this be? Oh my God. Well, this one was a puzzler for mathematicians for many, many centuries. We're going to see a video that attempts to address this question. But it turns out that it's possible to have different levels of infinity. There isn't a single unique infinity. there can be many different kinds of infinities, which is hard to imagine, but it's true. And we can prove it. So we'll see. No, there's one very cool video that will help explain it to us. And in fact, they do it in a very interesting way. They basically create a hotel with an infinite number of rooms, and they explain to you how this is possible. But don't you worry, we'll get to that one. We'll save that for another day. But today we have two very interesting videos which will help us understand the history of math. Now, here's what we're going to have to do. Now, I know this from past experience. If I try to show it to you on my screen, most likely you'll not be able to hear it properly. Also, if I show videos and they get recorded, I have potentially broken copyright law. So what we're going to do is this. We're going to go over here to Moodle. And what I'm going to do is open up this link. And I'm going to send it to you in the chat room. And what I'd like you to do is watch it on your computer, okay? So let me do that right now. Oh, wait a minute, I got the wrong one set up. All right, so it's 7 minutes long. So what I'd like you to do is watch it on your screen. I'm gonna stop sharing right now. Like I said before, we don't want to have any problems with copyrights. And when it's done, we'll get back together again and we'll talk about it. And I think you'll find it to be extremely interesting. All right. So here we go. Here's the link. Let me know if you have any trouble looking at it. And I'm going to turn off the screen sharing. And so why don't you go ahead and start watching it? All right, so is everyone done? Oops. All right. All right. Yeah, I don't want to rush anyone, but I'll give you a minute. So, um, that was kind of interesting, don't you think? Of course, when you stop and think about it, I mean, math itself arose because it was useful. People began to realize pretty quickly that they had to keep track of whatever they were doing. If they're farmers, for example, and so systems had to be developed to keep track of all this information. And in fact, a lot of these Babylonian clay tablets survived, and a lot of them are just very basic statements of transactions, purchases, and that type of thing. And so the later number systems, as he mentioned, the zero took a long time to come along because it wasn't really clear why we would even need a zero. So interestingly enough, the next video that we're going to look at is all about zero itself. They're going to explain to you, first of all, of course, how important it is, but also how it evolved over time to the way we use it now. So let me get you that link right now. Oh, I've got a ton of these. We're going to have a lot of fun with these videos, and because I think it's important to understand where a lot of this information is coming from and what it's really meant for. Not just to learn the techniques, which is of course important, but to have a broader understanding of the math and its background. All right, here we go. Now this one is called What is Zero? So it's pretty self-explanatory. All right, so let's check this out. All right, are we basically done? All right, well, now you have a newfound appreciation for zero, don't you? Man, did that turn out to be important. In fact, one of the reasons why we no longer use the Roman numerals is because of the lack of a zero. But yeah, the Indian mathematicians came up with the system that we use now. And so we've used it basically ever since basically the Renaissance, I guess. So that turned out to be a hugely important development. Now, we're going to see a video, not today, but soon, where they explain to us exactly why you can't divide by zero. So we know not to divide by zero, but we need to understand more at a deeper level why it's not possible to do this. And so the video that we'll be looking at does an excellent job of this. And it's also fun to watch. You'll see when we get to it. Sadly enough, we'll have to save it for another class, which reminds me, I don't know if you're aware of it or not, but next Monday is Labor Day. So that means we won't have a class on Monday. I won't see you guys again until Thursday. So, I know, try to hold back the tears and all, but so yeah, we just want to make sure that you, maybe you should be quickly reviewing the slides between now and then to make sure that you don't forget what we've been doing. But I just wanted to make sure that I reminded you. Okay, so in other words, when you do not see an invitation for Monday, that is the reason for it. In fact, I might even send out a reminder anyway by email, just saying, by the way, don't forget, no school on Monday. All right, so let's get back to the rational and irrational number. So basically, we know how to figure out if a number is rational. If it can be expressed as a ratio of two integers, it is exactly, or it is a rational number. But sometimes it's not as obvious as you might think if a number is rational or irrational. In many cases, it is. But there's certain techniques that we can learn to help us identify numbers that are either rational or irrational. So we're going to start by introducing some more definitions. When we have a number that has a fractional component, which means it's not an integer, what can happen is if you look at the digits after the decimal point, in many cases, there's a finite number of digits that come after the decimal. So for example, a number like this is referred to as a terminating decimal because there's only a finite number of digits after the decimal point. It's 5, okay? It's not infinity, as opposed to pi, or here's another simpler one. 1/3 is 0.33333. It does not ever stop, does it? In a case like that, we say that this is a repeating decimal. Because we need to express it not only with the ellipsis, but you notice the numbers are repeating themselves. And while we're on the topic, there's a special notation that you see sometimes in math that enables us to write this out without having to write a large number of decimals. This is often written as 0.3 with a bar over it. The bar means that the 3 is repeated an infinite number of times. Sometimes you'll see that notation. It's a quicker and cleaner way of writing something like this. The bar means 3 is repeated an infinite number of times. Okay, so these are two cases. Now, obviously, not all numbers fall into these two categories. For example, pi. What's going on with pi? Well, with pi, there's an infinite number of digits after the decimal point, but they do not repeat themselves. Okay, that's the key detail. And in fact, that's true for all three of these numbers, if you notice. It's not, these values are not terminating and they're not repeating. Okay, so that's what separates these from the numbers we're looking at right now, which are either terminating, which means they stop eventually, or they repeat themselves with an infinite number of values. So why does this matter at all to us? Well, oh, by the way, here's some more examples. These are all considered to be terminating because, of course, there's a finite number of digits after the decimal point. It doesn't matter how many there are, as long as it stops eventually. And these are repeating. Now, by the way, the repetition doesn't necessarily have to involve one digit. You notice here we have 1 5 1 5 1 5. So this first one could be written as 3.3 bar. This one could be written as 4.4 bar. And this one could be written as 2.15 bar, to remind us that it's both the 1 and the 5 that are being repeated an infinite number of times. All right, so with that being said, you'll see what this is leading up to in a minute. Terminating decimals can always be written as a fraction. No matter how many, and you can see it's actually not that hard to find one. For example, 0.8 is nothing but 8 over 10. 0.124 is 124 over 1,000. 0.3219 is 3219 over 10,000. Now that tells me that all of these the terminating decimals are rational. So in other words, these are all rational numbers, 0.8, 0.124, and 0.3219, because we can rewrite them as a ratio of two integers. So even though they may not look at, these are all rational numbers. Now, certainly you can reduce these, but there's no point. Like for example, the second one is clearly 62 over 500. It doesn't matter. You only need one ratio to prove that they're rational. Okay, now. What about the repeating decimals? Okay, so we now know that in these two new categories, the terminating decimals are always rational because they can be expressed as a ratio of two integers. How about the repeating ones? Well, it turns out that the same thing is true for the repeating decimals. These can also be written as a fraction, but it can be very tricky to do it. Okay, so in other words, a repeating decimal can also always be written as a fraction, which implies that a repeating decimal is also a rational number. The question is how, though? Like, imagine you've got something like this. We can see for ourselves that it's repeating and it can be expressed as 0.87 bar, but how in the world would you reduce that to a ratio? All right, so what I'm going to do is show you one quick example of this, a very simple case. I don't want to get too far ahead here because, like I said, we're going to be off on Monday, and by the time Thursday rolls around, we'll probably have to repeat some of this anyway. So I just want to show you one quick example, and then I guess we'll call it a day, sadly enough. I know it's hard to stop when you're doing math, but we do have to stop. So here's what we're going to do. Let's do this example, 0.8 bar or 0.88888. how do we know that this is a ratio of two integers? Well, here's our strategy. We're going to do this. It's a two-step process. Number one, let's just call this n. N is the variable that represents 0.8 bar. No problem there. Now, here's the clever part. If n is 0.8 bar, what is the value of 10n? Oh, okay. So in other words, if n is this, if I multiply this by 10, look what happens. Aha. Now, how does this help me? Because look what I can do now. I can subtract one from the other. Okay, so let's see what would happen if I subtract one from the other. It will leave me with a nice, clean result. Watch this. So I'm subtracting, and I get 9n equals 8, or okay. So in other words, 0.88888 or 0.8 bar is nothing but 8/9. And if you don't believe it, you can put this into your calculator and you'll see that that's exactly what's happening. So what that proves is that this number is a rational number, because I just proved that it's equal to 8/9. Wow, that was clever. Does that mean our heads are spinning from the cleverness? Yes. Now, what I'd like to do, and like I said, I'd like to save this for next time, since we're going to have time off anyway. I'm going to show you some more complicated cases, but in each case, the logic is very similar. But here's the conclusion that I want you to take away from this. If we have a decimal, any number which is a decimal, in other words, it's not an integer, if it is not terminating or repeating, that guarantees that it is irrational. And that's why pi is irrational, because it is not terminating and it is not repeating. We have an infinite string of digits that are not repeating. Okay, so terminating, decimal, and repeating decimals are rational. All other decimals, by which I mean non-integers, okay, so that's the hint. So now, armed with this information, we can identify any number we may encounter as either being rational or irrational. Okay, so what we're going to do when we come back again on Thursday is we're going to go back and dive back into this again and learn a little more about it. We're going to see a couple of videos. One of them will explain why we can't divide by 0, and one of them will also explain why the existence of irrational numbers caused so much trouble for the ancient Greeks. Okay, you'd be surprised how much trouble this represented for them, because it basically violated some of the assumptions they'd been making about how the universe works. It basically was proof that they were wrong about certain key ideas. And that's why it upset them so much. But anyway, we'll save that all for next time. You got a lot to look forward to. Let me put it that way. And in fact, I hate to keep you in suspense, but can you all hold out until next Thursday to learn about these key ideas? Can you wait? Okay. All right. That's good. All right. Will you fret about it the whole time? No. Okay. That's good. So yes, so we'll stop right here. And as usual, the recording will be made available on YouTube. And what you might want to do is flip through these slides before we meet again, just to make sure we remember what we've been doing and understand it. But other than that, you can have a fun 3-day weekend. And I'll see you all next Thursday. All right. Okay. So if there's no last minute questions, I will see you all next week.
Thank you.
Hey, you have a good weekend.
All right.
All
you're
right,
welcome.
take care. Have a good one.
Okay. Bye.
Have a good weekend.
Okay. Bye.